I grew up in Ithaca, New York in the US, where there's a huge variety of landscapes. There are farms and forests and mountains and lakes and massive waterfalls all within a pretty small region. But swimming in the Finger Lakes right in my backyard in the summer, or visiting New York City on field trips, I had no idea that the land I was walking on was actually shaped by glaciers. We'll come back to New York later, but it won't be our only example because actually many of the Earth's landscapes were shaped by glaciers in some way or another millions of years ago. And today, they're like icy 21st century canaries in the coal mine, warning us about the massive changes to our world that are coming as climates change and sea levels rise. These behemoth globs of compressed ice and snow moving across the land created fertile soils and physical features while also serving as frozen time capsules. They recorded both Earth's climatic history over several million years and contain clues to its climatic future. I'm Zachariah, and this is Crash Course Geography. Our journey through physical geography is almost over, and by now we definitely know the Earth is ever-changing. And glaciers have often been a crucial part of that change. Basically, a glacier is a large mass of ice that formed from compressed snow that moves thanks to its own weight and the pull of gravity. And there are actually two main types. When we find a glacier in a mountain range, it's called an alpine or mountain glacier. And on a larger scale, a continuous mass of unconfined ice bigger than 50,000 square kilometers is called a continental glacier or ice sheet. In 2021, about 10% of the Earth's land surface is ice. Most of that's found in the Greenland and Antarctic ice sheets. And glaciers have a big influence on our global climate. Because glaciers covered in snow are so dazzlingly white, they reflect a lot of the solar radiation they get, keeping the Earth cool. And we saw in our weather episodes how the enormous temperature difference between the polar regions and the warm equatorial regions drives the system of heat transport around the world. And like we learned in our last episode on groundwater, only 2.8% of the Earth's water is freshwater. A tiny bit of that is in lakes and rivers, and almost a third is groundwater. But all the rest is locked in glaciers. So if all the world's glaciers were to melt, sea levels would rise about 70 meters, changing ocean circulation patterns, which would alter weather and climate in the mid-latitudes. Not to mention create political, economic, and social upheaval, dramatically reshaping coastlines and the lives of over 2.4 billion people who live within 100 kilometers of a coast. Looking to the past, it was glaciers themselves that provided the first inkling there had been big changes in global climates throughout Earth's history. Many naturalists, and even a poet, during the early 19th century were struck by the fact that the British Isles and the North German plains, which are areas far from glaciers even today, had deeply eroded U-shaped valleys, massive erratic boulders far from where they formed, and bedrock that was smooth like it'd been polished by abrasion. These features were similar to what was seen in the Alps where there were still glaciers, and they concluded that it was evidence that the British Isles and North German plains also had icy pasts. Today, we know the most recent ice age is one of several ice ages that Earth has experienced in its long history. And it doesn't mean that Earth has to be entirely covered in ice. An ice age alternates between glaciations, or a period when temperatures drop and ice sheets grow and spread outwards over vast areas, and interglaciations, when the climate is milder. And this back and forth between glaciations and interglaciations means an ice age can last for millions of years. Right now, we're actually still in an ice age. We're just in the middle of an interglaciation. Evidence from deep sea sediments actually shows that our ice age started when glaciers started growing about 2.5 to 3 million years ago. Both ice sheets and mountain glaciers were forming at this time, but they have some pretty specific requirements. They form above the snow line, or the lowest elevation where there's ice and snow all year round. So where the amount of snow that falls each year is more than the annual ablation, or how much is lost by evaporation and melting. Then, as layers of snow get buried and compacted into ice, the weight of the glacier reshapes and realigns the crystals, making them harder and denser. When the ice is about 30 meters deep, the millions of ice crystals in the bottom layers change form and become plasticky and can glide over each other. Which means that from this depth to its base, the glacier behaves more like silly putty and sort of stretches out, carrying the brittle ice on the surface. So a glacier is not just a hard block of ice that slides down a slope. Glaciers usually flow slowly. Large ice sheets move a few centimeters per day and flow out in all directions, while active mountain glaciers can cover several meters each day as they're pulled downhill by gravity. It's really weird to think about, I know. But glaciers don't flow like rivers. They move much slower, but with tremendous energy, meaning they do a ton of work as they engulf and dramatically reshape the landscape, dragging everything in their wake. When a glacier stays more or less the same size, we say it's in dynamic equilibrium, because the amount of new snow is about equal to how much is melting. But when climate's warm or there's less snow, glaciers retreat and grow smaller. Ultimately, when there are very few or no glaciers on the planet, we consider the Ice Age over. We're not quite to that point yet, so we're still technically in an Ice Age. Remember, I said we're in an interglacial period of this Ice Age, meaning there are a lot fewer and smaller ice sheets in glaciers on Earth compared to their greatest extent about 20,000 years ago, known as the last glacial maximum. At that time, much of North America, Europe, and southern South America were blanketed in extensive ice sheets and glaciers, which got to be more than 3 kilometers thick in parts of Canada and the US. And when this sheet of frozen water began to melt and retreat quite rapidly some 15,000 years ago, it left behind a ridge that was basically a jumbled heap of gravel, sand, silt, and clay called a terminal moraine. It still stretches more or less continuously across North America from the Puget Sound in Washington state to its southern limits in Midwestern states like Missouri and Nebraska, all the way to Montauk Point on New York's Long Island. The ice sheet even shaped New York City as we know it. Original settlers of the area, the indigenous peoples of Algonquin-speaking languages, utilized features carved by glaciers much in the same way we do now, using the waterways for trade and commerce and ridges as easy paths to walk between villages. In fact, if you've ever walked down Broadway, then you've walked down one of these trade paths. In neighborhoods like Brooklyn, Queens, and Staten Island, terminal moraine forms the high ground. Initially, as the city grew, these sites were ignored for homes and other buildings because they were stony and inaccessible, and construction was difficult. Instead, this land became parks, cemeteries, and golf courses. Even today, these remain the more densely wooded and landscaped sections of these neighborhoods, and are now some of the most attractive locations in these boroughs. But back to the ice. Like a giant bulldozer as the glacier moves forward, it drags along everything in its path, picking up tiny pebbles or enormous boulders often the size of a school bus. When it melts, they're left strewn across the landscape as though flung by a giant playing marbles. And Central Park is full of these stray boulders called erratics because, well, they're erratic. They're far from where they would have originated and have different compositions from the surrounding, often younger rocks. Boulders like these were what some of the naturalists were noticing over in Europe. Moraines and erratics are what we call depositional features, which are features formed from the debris carried by ice as glaciers melt, and they still influence how the land is used today, like we saw here in New York City. So glaciers can be like huge excavators, hauling debris from one place to another, adding features to the landscape as they melted and retreated. But they also change the land through erosion as they advance, like the Finger Lakes in central New York. Their distinct, elongated basins were eroded and deepened by ice sheets. And the Great Lakes are actually former river valleys that were greatly enlarged and gouged out by glacial erosion. The bedrock beneath each lake is covered in thick blankets of glacial deposits, which are the bits of rock fragments that the ice picked up as it moved. And as the ice sheet retreated north, meltwater filled in the depressions, forming the Great Lakes. Mountain glaciers have also sculpted majestic landscapes in regions like the Himalayas, Sierra Nevadas, Rockies, Andes, and Alps. Like the Matterhorn on the Swiss-Italian border is the iconic image of the Alps. Its symmetrical spire with precipitous rock walls is a siren call for climbers everywhere, and is the work of glaciers. To start out, we have a mountain glacier, slowly advancing down the mountain slope. As it moves, blocks of rock that have been loosened by weathering get removed or plucked out as part of glacial plucking. Partnered with abrasive rock debris sandpapering the landscape, this forms an armchair-shaped hollow in the side of the mountain called a cirque. When the ice in two adjacent cirques eats away at the ridge between them, it forms a sharp, often serrated ridge called an arête. And when 3 or more cirques carve away a mountain mass from different sides, we eventually get a horn or pyramidal peak, like on the Matterhorn. But the work of the mountain glacier isn't done. As the ice grinds over uneven bedrock and the glacier is stretched as it flows over a convex slope, deep vertical cracks called crevasses open up on the brittle ice on the surface as a response to the stress. Debris that gets left behind can form ridges along the side of the glacier, which we call a lateral moraine. And where 2 glaciers join, their lateral moraines merge to form a medial moraine. Often moraines dam the foot of a cirque, encasing small, shimmering mountain lakes called tarns, which are among the most popular destinations for backcountry hikers and campers. Further down, a glacier moving through a valley will usually erode the walls and deepen and broaden the valley from a V-shape into a U-shaped profile. These glacial landscapes that have been left behind after the last warming are home to millions of people in Eurasia and North America. They've been plowed to produce crops, dug into for sand and gravel, and paved over by concrete and tarmac. Lately, when we hear about glaciers shaping the Earth, it's because they're breaking. Like in 2021, data from uncrewed submarines showed that warm water may be weakening critical stability points of the Thwaites Glacier, which is also part of the West Antarctic ice sheet and known as the Doomsday Glacier. When it breaks, it could raise global sea levels by over 0.5 meters and potentially collapse the entire West Antarctic ice sheet, which would flood lowlands and islands across the world. So the story of ice seems to be closely tied to our human story. Ice has advanced and retreated over time, but when the climate stabilized after the ice started melting 12 to 15,000 years ago, agriculture flourished. And many nomadic groups shifted to more settled lifestyles, setting the scene for many of our societies today. And as the ice melts further, our lives could shift again. So as we contemplate that future, join us next time for a look at the geography of natural hazards. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn more about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide. Thanks for watching this episode of Crash Course Geography, which is filmed at the Team Sandoval Pierce studio and was made with the help of all these nice people. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon.